Hello everybody! Today we're going to try out how you can make assumptions easily and free of charge about an existing building using a 3D Google Maps section. The Google Maps section contains enough information about the shape and the facade of the building that we can use to deduce the supporting structure and floor areas. This means that even without being on site or having access to the plans of the building, we are able to create an approximate CAD model of the building stock. Here's a short summary of the steps we will take. We will first need to install Blender, then download the Blosm add-on and install it to Blender. Using the Blosm add-on, we can then import 3D map tiles into Blender and export them with texture as an FBX. Afterwards, we import the FBX into Rhino and create a CAD model. I'm using a 3-month trial version of Rhino, so I'll show you this workflow using Rhino as an example. But you can also import the FBX into many other tools and work on the CAD model there. I've added a link to my file in the description so that you can use it as a comparison. The folder contains the file in many different formats. I hope there is a suitable format for the program you're using. Okay, let's get started. The first thing we need to do is download Blender, a free 3D program that we can download from the internet. I'll leave the links to the programs in the description below. When you're on the Blender website, scroll down and click on Download. Make sure you choose the right version for your computer. There are 2 for Apple and a lot of other options for other operating systems. Then open it in your downloads and install it. Alright, now we open Blender. In this window, we can leave all settings on default and save the preferences. Then choose General File and delete everything from the template file by selecting it and typing X and push Enter. Now we need to install the Blosm add-on. You've got the link in the description. We are going to take the basic version of the add-on, which is enough for the things we want to do. In this box here, we can donate an amount to support the people who developed this add-on, which is very cool. If you don't want to donate, write a 0 in the box. Now you will need to enter an email address, and if you have chosen to donate, you got to enter the payment details here. Then click Get, and the add-on will be made available for download as a zip file. Okay, open the Blender window again. Make sure you get the zip file in your downloads. Then we go to the Edit tab and go to Preferences. Here in the top right corner, we select Install from Disk. We go to our downloads and select the Blosm zip file. To enable the add-on, we need to tick this box here above. Now, to be able to import data from Google Maps, we need to specify a location for this data on our computer. I'm just going to choose the desktop for now. Then we only need the API key to import the data. To create one, click here on Get It. Now we are redirected to the Google Maps platform. We need a Google account for this step. I'm already logged in with my Google account and have chosen a free trial version. If you need help with the registration, I have put a link to a video in the description. The guy who made the video goes through the registration process with you step by step. Once logged in, we go back to the Blender window, go to Preferences and click again on Get It. Then scroll down and click on Go to the Credentials page. Then we need to go to APIs and Services and make sure the Map Tiles API is enabled. When we're ready, we go to Keys and Credentials and click on Create Credentials at the top. We select API key here. Now you can restrict where and for which APIs your key can be used to prevent unauthorized use. Then click Create. Once the API key is created, we can copy it here and go back into the Blender preferences. We enter the API key here and close the window. Then click this tick here in the top right corner to open this little toolbox. Click on the Blosm tab. We will now see the Google Map coordinates and many selection options. To choose the area you want to import, click here on Select. We are then redirected to a page with a world map, where we can choose any area. To see the selection box, press Show Selection Rectangle. Make sure your selection is not too large so that your computer can still handle the file size. Of course, you can always import more than one tile and put them together to get a larger area. You can try it out a bit and test the limits of your computer. Once you have selected your area, press Copy and go back to the Blender window. To insert the coordinates here, click Paste. Now they have updated according to our selection. There are many ways to import the map model, for example as a clear geometric mass model or as a scanned model with Phototexture. There are more options, but we'll try the scanned model today. To get the scanned model, choose 3D tiles here, and for the level of detail, select buildings with more details. Then click Import. This usually takes a bit longer, but I skipped the import time here. That's the scanned model. And if we switch the viewport mode to shaded, we should see the model in color now, with all its textures. The quality of the texture is not perfect, but it tells us a lot about the buildings, and we can easily make assumptions about the internal structure of the buildings just by looking at the facade. Okay, this is in Blender, so we're still not in Rhino. We first save the file as a blend file. Then we need to somehow export this file with materials. I tried a lot of different ways to do this, and the best one I found was to export it as an FBX file. We can import an FBX file into Rhino or other tools later, but to export it we have to fix the materials first. So if we bring up this window here, go to the drop-down menu and click on this shader editor, we'll see that we have a shader for the model that looks like this. And if we have a look at the materials here on the right, we'll see that every single material has got the same one. But this material is not going to be recognized in Rhino. So we need to use a script to optimize this material and create a material that will be recognizable later when we export the FBX. We won't do this manually because it would take too long. We do this using a Python script. I'll add the link to the Python file below. So now we need to expand our window. There's a little sign here that allows us to open another window. We change the contents of the window from shader to text editor here. Then click on text and open the Python file. You should now see the whole script in this window. Watch what happens here on the right with the shader when we run the script. To run it, click on this play button here. We can see that all the materials are now modified. We have the principal BSDF material. And this is the material that's going to work with our export. Okay, let's do the export. We first save the file. Then, to save the materials, we go to File, External Data, and Unpack Resources. Here we need to choose Use Files in Current Directory. Okay, now we do the export as an FBX file. Select the model, go to File, Export, select FBX, and limit the file to selected objects. You can leave the other settings on default and export it. We should now be able to find the FBX file plus a folder containing all the texture images on our computer. Well, now open a new model in Rhino. As I mentioned before, I'm using a free trial version. I'll add a link below. Then just drag the FBX file into the Rhino window. Choose Import File and apply. The default settings should work for us here. At this point, I think the units do not match, but we'll sort that out later in the settings. Importing can take a few minutes, depending on the size of the model. Okay, often you cannot see the model directly in your window because it has landed somewhere in the file. When that happens, click on the magnifier with the two yellow circles inside. This tool is very useful if you have lost an object somewhere in the file. Change the viewport from wireframe to rendered, and we can see the complete model with texture. That's the building I'll focus on. It's in the center of Cologne. Okay, it's very important to prepare the file before we start working on the CAD model. The first thing we are going to do is align a temporary C-plane to the building so that we can draw at right angles and the view isn't always north facing. To do this, we draw a line on one side of the building. At this point, we briefly check the units, because sometimes they're set to millimeters. Check the length of the line by selecting it, typing length in the command field and hit enter. We can see the result here. To change the units, we go to the file settings. Go to File in the top left corner, choose Settings, then go to the unit settings and change the units from millimeters to meters. You will now be asked if you want a 1 millimeter box to become a 1 meter box, or if you just want to change the units and keep the size of the model. We choose the second option and apply. Then we go to the C-plane tab and use this tool with the 2 points called C-plane by X-axis. The tool first asks you to choose the C-plane origin. Then it asks you to choose the X-axis direction. Now go to the drop-down menu, set camera and choose C-plane top. You'll see that the view is now perpendicular to your building. To save the C-plane, click this button here and name it. Then you will always be able to find it under Set C-plane in the drop-down menu. We also need one C-plane for each side of our building. When a C-plane is switched on, it functions like a drawing layer. It is therefore much easier to create a grid and work in 2-dimensional views instead of 3-dimensional space. To align the other C-planes, we'll set some clipping planes first. Type clipping plane in the command field and follow the instruction of the tool in this window here. You can also create vertical ones in the top view by clicking vertical and making 2 points. Then you gotta change the viewport and set a third point. Whatever you do, you can always press Shift to stay in ortho angles. Once you have got one of these vertical ones, you can copy it to each side and rotate it by using the rotate command. If you don't have these XYZ arrows to move an object, you can turn on the gumball here and you should be able to see it now. You can change the direction and the visibility of the clipping planes in the properties. Then we use our clipping plane collection to create the other C-planes. Write named C-planes in the command line and there will open a toolbox at the right. In this toolbox you'll see all the named C-planes you have. Okay, now we use the C-plane to object tool. Select one of the clipping planes and click this little icon with the cube. The C-plane is now in the same place as the clipping plane. To save the C-plane, you can just push this button with the little plus and give it a name. We're gonna do this procedure for each side of the building. In my case, the building is almost at right angles to the cardinal directions. That's why I named the individual sides of the building like this. But you can give them whatever name you want. To activate a C-plane, double-click on the C-plane in the toolbar. Keep these 3 C-planes because we want to be able to return our model to the north at the end. When your collection is ready, create a collection with all the named views you'll need. Go to the drop-down menu, set camera, and choose one of the given options. For example, C-plane top, C-plane bottom, etc. Then go to the View toolbox by clicking on the little camera icon. To save a named view, push the little plus symbol here and name it. I do that for each side of the building, activating a C-plane and finding the right view. To work with these views, you can double-click the one you need. It works the same way as the C-plane toolbox. Once we have prepared the file in this way, we can start working on the grid. I select the appropriate C-plane and the view I need. I also clip away the foreground to be able to see the complete facade. Then I start with a horizontal line and check its length. I divide the length by the number of windows to get the distance between the vertical lines. For all values that we take out of the model or set as a distance, we round up or down to avoid completely crooked numbers. Now I align the verticals using the array tool. When you're using the array tool, the directions of the axis depend on the current C-plane. So sometimes you gotta change the C-plane before, or check which C-plane is currently active and see how the X and Y axes are positioned right now. I continue with the horizontals. I place one at the top and one at the bottom of the window, and then array this package. By changing this number, you can readjust the distance between the elements. It is important to note that the photo texture is often distorted towards the bottom. It is based on aerial photographs and therefore becomes increasingly inaccurate towards the ground. So I try to create my grid based on the upper part of the building. I also have to say that whatever we do here, of course we can only approximate. It's not a question of being able to make really precise statements, but of getting as close to reality as possible. We want to be able to make statements about the supporting structure, locate the development core, and map the spatial organization. For these aspects, this degree of accuracy is completely sufficient. I create this grid for the two different sides and copy them to the other ones in the top view. I move the grid to the layer of the facade so that I can combine the two sides to create the horizontal grid for the roof. Using the array command and the distance from the facade elements, we can then easily create it. In order not to forget the context, I fade in the surroundings again by deactivating the clipping planes in the perspective. Oh, I think I copied the grid at this side once too much. Okay, now we have the most important parts of the grid, but we're still missing the outlines of the building. To get these outlines, I hide the upper part of the scan model so that I can see all the lines of the horizontal grid. To hide something, you can just type hide in the command field, and if you want to show it again, you type show. At this point, it might be helpful to look at Google Street View to see if you can make out anything of the supporting structure. The building I focus on is a bit hidden in the backyard. But I think I can see a covered ceiling here, and here are some round columns. I can also have a look at the facade, but right now I'm more interested in the elements of the supporting structure. I made some screenshots to see if zooming in helps to see more. These parts here of the photo are very dark and it's hard to see anything. Maybe it helps to open them in Photoshop or any photo editing program to play a bit with the brightness and the gradation curve. I just tried out a few things and it really helps to see it clearer. I can only estimate the dimensions and consider how thick the individual ribs of the covered ceiling could be. I think in this case a rib could be about 20 centimeters thick. Okay, I close all the windows and I start to construct the ceiling. I draw the outlines, create a surface and extrude the surface. I guess the height of the covered ceiling could be about 50 centimeters. In order to be able to make more precise statements about the dimensions, you can look for escape plans, for example, or search for the building on real estate portals, or you could take photos and measure parts yourself. You could use all the options you have, but I will try it out without having any further information available. What we have is very good. We'll deal with the heights later. For now I put it here. I activate the clipping planes in the perspective and move them a little so that I can see the entire lower part of my building. Of course, you can also create a new clipping plane each time, but to keep it clearer, I usually use as few as possible. So I move the ones I already have. I also clip away the bottom of the model to have a better inside view. The back of the texture shows the same as the front, which sometimes helps to build the model. Okay, then I go to a side view and create the grid for the lower part. I can base it on the upper part grid and just copy it down. Then I extend it by using the commands scale 1D and array. Now I'd like to make the outline of the lower part. Sometimes it also helps to look at Google Earth for more details. The texture of the Google Earth model is much more accurate than ours, so you can often find helpful information there. I can count the individual facade elements and look at the exact course of the facade. Some elements are kind of hard to see, but maybe I can guess it using the grid I already got. To construct the three-dimensional ceiling, I used the same tools as last time. Drawing the outlines, then creating a surface and extruding it. A good grid is worth a lot because everything that follows is based on it. Once the grid is ready, we can start positioning the columns. To find out where the supports are positioned, we take another look at Google Earth. I can see a few supports here and consider how they are positioned in relation to the facade elements. Here I think I can see that they are centered. I can also count them and see approximately how far apart they are. Okay, I draw the first circle, create a surface, array it, and then extrude it. Since I assume that they are each centered in a field, I need a support that transmits the force of the column to the cassette ceiling. So I draw a rectangle and extrude it. I array it so that all the spots above the columns have this support. Then it is a matter of determining the story heights. I first copy the columns and the ceiling ones. Here I can already see how the CAD model fits into the scan envelope. Let me turn this C-plane on to see it better. Alright, then to see the inside of the model, I move one of the clipping planes through it. I move the ceiling down to a place where it could be positioned approximately. To use the parapet height as an orientation, I first create a floor on the top of the covered ceiling. Then I can assume a parapet height of between 90 and 110 centimeters from the floor. I move this package up to the bottom edge of the window and set the story heights that way. I copy it to the next window and measure the distance between the floors. Then I round the number up or down and array the others. I select the columns with their support elements and array them in Z direction. Okay, let me turn this clipping plane off so that we can see the whole model with the scan envelope and the CAD model inside. Alright, let me change the viewport to ghosted so that we can see through the scan. Now we've got the ceilings and the columns, but we're still missing bracing elements and infrastructure like fireproof stairwell or bathrooms, for example. So let's assume that there's a core in the middle of the building. I'm going to turn on the environment again to have a bit more context. And I switched the viewport mode to render to have a look at our roofscape. I think that's the area where the core is located. In the top view, I can see something like a rectangle, and there are these two cylinders at the roof. At this point, we can also have a look at Google Earth to see if we can find more details about the core. Okay, we have the two cylinders that I think do not go through. They are partially cut off here. And we can see some walls and doors. We can also make out some roof bonnets and the smoke extraction. Here it is also important to pay attention to the facade and the position of the elements in relation to the facade. Let's go back to our model. Okay, we assume that the walls we were able to see were the outer walls of the core, more or less like this. Then we have a look at our grid and see how this rectangle fits into it. I draw the outer walls then, again estimating a thickness of 30 centimeters or something like this. Then I create a surface, put the surface in the correct position and extrude it. Now we are able to see the complete horizontal and vertical supporting system. I changed the viewport mode to Arctic and hide some of the scan elements to have a look at our skeleton. The inside of the core is hard to see, but I felt free to try a version and it could work like this. There are some toilets, a storage room, an elevator shaft into which 2 elevators would fit, and a fireproof stairwell. I arranged it that way, but probably there are many other ways to fit these functions in the core. It's not necessary to have the exact arrangement in order to continue working with the model and using it for designs. And at the end, thanks to Dusan Čeković from the How to Rhino community. Thanks to the people from Prochitecture for the Blosm Add On. Thanks to Tony, who helped us with the registration process on the Google Cloud platform. And thanks to Fredrik Lindgren for the Python script. If you have any questions, remarks, or tips, please use the comment function below. And that's it. Have fun trying it out.